In this video, we are going to discuss the difference between ionization energy and electron affinity. So, ionization energy is defined as the amount of energy required to remove one electron from an atom in the gaseous single state, from the single gaseous state of the atom. So, we have something like atom X. When we put in energy, this gives us the cation plus an electron, but X has to be in the gaseous state. So we get the corresponding cation from the atom by applying some energy to remove one electron and to get the cation or the positive ion of this atom. And this ionization energy is called the first ionization potential. So this one is the first ionization potential or first ionization energy. If we want to further eject or remove one electron, so we bring this X positive or the cation and we put in energy to give X2 positive plus the electron. So we get an ion with 2 positive charge. So this is the second ionization potential or second ionization energy. If we want further to remove another electron, we put in more energy to get a positive charge ion with 3 positive charge plus an electron. The major difference between first and second and third ionization potential is the first ionization potential is smaller in value compared to the second, and the second ionization potential is smaller in value than the third ionization potential. So we can just describe it as this. This is the first ionization potential is smaller in value than the second ionization potential, and the third ionization potential is the greatest in amount. And this makes sense, as you have here in the atom X. It's relatively easy to remove an electron because it's not positively charged. But when you look here at X2 positive, that means you have to put in more and more energy to remove an electron from an ion which has a very high effective nuclear charge. The effective nuclear charge in X2 positive is really high. That means the outermost electrons, are tightly bound to the nucleus. And this makes it really hard to remove that electron. In the periodic table, the ionization potential increases throughout the period. So the ionization potential in the periodic table increases. But in the group, the ionization potential decreases. And that makes sense. For example, in the alkali metals here, the atomic size is greater than the 2A elements, and we decrease the atomic size as we go from left to the right. So you have smaller and smaller atomic size as you go from left to right. And when you have smaller atomic size, that means you have very high, and that means you have a high effective nuclear charge, and that means the electrons are tightly bound to the nucleus, and that will lead and that will need more energy to remove that electron, which is tightly bound to the nucleus. So the ionization energy will increase. But in the case of the group, when you go down the group from top to bottom, that means the atomic size increases as you go down the group, and that means the effective nuclear charge decreases and the electrons are not tightly bound to the nucleus. So it will be easier to remove one electron from an element such as cesium, for example, because of its atomic size, small effective nuclear charge. Whereas it will be harder to remove an electron from a fluorine atom because of the high effective nuclear charge of the fluorine atom. So you will have to overcome this great attraction forces from the nucleus to the last electron. But there are some anomalies to this case. As we can see here in the nitrogen 7 and oxygen 8, oxygen should have a higher ionization potential compared to nitrogen because as we go from left to right, the ionization potential increases. But if we look carefully at the electronic configuration for each nitrogen and oxygen, we find out that the oxygen atom can remove one electron. We can remove one electron from the oxygen atom easier compared to removing one electron from the nitrogen atom. So let's do the electronic configuration of both nitrogen and oxygen. So nitrogen 7, let me draw it here. Nitrogen 7 is 1s2, 2s2, 2p3. Whereas oxygen 8 is 1s2, 2s2, 2p4. So we have 2p3 here, like, let's draw it here. 1, 2, 3. So we have 2p of the nitrogen. 1, 2, 3. So I have distributed the 3 electrons of the nitrogen. Whereas the oxygen, if I configure the electrons in the oxygenate here, 1, 2, 3. So that should be 1, 2, 3, and 4. And this is the 2p. So look carefully here. You have 2p, the 2p of the nitrogen. Look carefully at the 2p of the nitrogen and look carefully at the 2p of the oxygen. So when you remove one electron from the nitrogen atom in the 2p sublevel, this will lead to a breaking of an electronic system which is half filled with electrons. So the 2p sublevel here was half filled with electrons. Your sublevel is stable when it's half filled with electrons or completely filled. So you have stable sublevel. If it's completely filled with electrons or half filled with electrons. And now you destroy this stability, so it will need much higher energy to remove this electron. Whereas in oxygen, actually you remove one electron, and this electron is the last electron, which is this one. So you will have 3 electrons here, right, in the 2p. And this will lead to a higher stability. So it's actually preferable to remove that electron because you will get a half-filled system with electrons.